Welcome again to Let's Talk Advanced Chemistry with Pastor Dan. We're going to take what we looked at before in thermochemistry and we're going to make it a little bit more advanced. We're looking here at calorimetry. Now, calorimetry has to do with the calorimeters, the things that absorb energy inside of the system. Calorimetry is defined as a measure of heat flow. And the calorimeter is a device to perform the calorimetry. And if we have a bomb calorimeter, it's a type of calorimeter that exothermic reactions can take place, which can absorb a great deal of heat. So that takes us through our first concept there. Now, in order to do that, we're going to take what we did, and actually the other concept we didn't talk about, heat of fusion and heat of vaporization, we're going to include that as well. So, looking at specific heat, again, the amount of energy needed to bring a gram 1 Kelvin, 1 gram of substance by 1 degree Celsius, 1 Kelvin, same value. A Kelvin at a degree Celsius, same thing. Okay, equation now. I'm making it Q instead of delta H because this is Chem 2, this is advanced chemistry. It's equal to M times C times delta T. We also, last year, we didn't discuss it this year, but I'm going to show it to you now. Heat of fusion and heat of vaporization. Heat of fusion, again, is the amount of energy needed to melt 1 gram of a liquid. Now you'll notice there's no delta T and there's no change in temperature because when you melt, you're at a constant temperature. Temperature remains constant. So the Q of F is equal to C of F times M. In heat vaporization, it's the amount of energy needed to boil 1 gram of a substance. From a liquid, melting from a solid to a liquid, boiling going from a liquid to a gas. All right. And those are our equation. Q of F is equal to C of F times M. Q of V is equal to C of V times M. All right, so if you need to pause the video and write this all down, that's fine. Okay? So we're going to take one problem and work it through. Now, we had these from last year. The C of F of ice is 336 joules per gram. The C of V of ice is 2,270 joules per gram. We talked before the specific heat of ice, which is 4.184. The specific heat of water. The specific of ice, solid ice, is 2.01 joules per Kelvin. Now we can also do degrees Celsius. That's what we're going to do. And the C of steam is 2.00 joules per gram, degrees Celsius or Kelvin. So I want to take a problem. I want to find my energy needed to convert 134.90 grams of ice at a negative 23.99 degrees Celsius to steam at 135.99 degrees Celsius. All right, so we're going to start. So basically what we're looking at here is we're doing 5 steps. First, we have to heat the ice. Then we have to melt the ice. Then we're going to heat the water. Then we're going to boil the water to steam and then heat the steam. So there's going to be 5 processes in this situation. So we'll start with ice, the Q of ice. Now remember we said from the equation, it's M times C times delta T. The mass here, 134.90 grams. The specific heat of ice, as it says up here, is 2.010 joules per gram. And I'm using degrees Celsius, easier now, just to work through. And the delta T. Now, we started at negative 23.99 degrees Celsius, and we went to 0. So that change is 23.99. If we add those together, we have 134.90 times 2.010 joules per gram degree Celsius, 23.99. We get 6,505 joules. We got 5 sig figs, infinite, that's a constant, and 4 sig figs, so 4 sig figs the answer, 6,505 joules. Now we're at the second step. We're going to melt it. Now it's not having temperature change. We're going to do the Q of F, heat of fusion of ice. So that's going to be M times C of F. The mass doesn't change. It's still going to be 134.90 all the way through. That mass is going to remain the same. But the C of F is 336 joules per gram. So grams across out will be in joules. 134.90 times 136, 5 sig figs, infinite sig fig is a constant. We're going to get 4 45,326 joules. All right, now with that second step, now we're going to heat the water. Water, the Q of water is going to be M times C times delta T. My mass is going to remain the same. It's not going to change. It's still 134.90 grams. Specific heat of water is now 4.184 joules per gram degree Celsius. And the temperature is 100 degrees Celsius. So from 0 to 100 degrees Celsius, that changes 100 degrees Celsius. Now, how many sig figs we have? We have 5 sig figs here. Remember that 9 is after, 0 is after a number and after a decimal, showing exactness. So we have 5 sig figs. 4.184 is a constant, so if it's significant. And here we're going from exactly 0 to exactly 100, so it's exactly infinite sig figs. So 5 infinite, I have 5 sig figs. Take your calculator, multiply through, you should get 56,442 joules. Now with that step here, now we're at melting, this D process. All right, so we're going to do the Q of V.
Sorry, boiling, not melting.
Remember we said from the equation Q of V is equal to M times C of V. The mass doesn't change. Mass is still 134.90 grams, but the C of V, heat of vaporization, 2,270 joules per gram, grams across out. 5 sig figs, infinite sig figs, 5 sig figs. The 5 sig figs, I should get 306,220. Remember, we have to cut off to make 5 sig figs. Answer is joules there. Now we're at the last step, we hit the steam. All right, so Q of steam is equal to M times C times delta T. Mass is not going to change. Mass is still going to be 134.90. We said Q of steam is 2.00 joules per gram degree Celsius. And we're going from 135.55, sorry, from 100 to 135.99 degrees Celsius. So the temperature change there is going to be 35, not 135. Be careful. I often have students make that mistake. It's from 100 to 135. So the difference there is 35. 4 sig figs again, infinite 5, least number is 4. So we get 9,710, but that 0 is significant, so we put a bar there. All right, now we're going to add them up. So if we add them all up, remember it's the last filled column, answer is going to be 424,203 joules. And that's the total amount of energy needed to heat ice at a negative 23.9 degrees Celsius to steam at 135.99 degrees Celsious. All right, we'll try this again, okay? So that way we'll work through this. If you want to try it on your own, great. If not, we'll do it together.
So if you need to pause and work it on your own, that's fine.
We'll do the same process. So we're going to start with Q of ice. Okay, so that is going to be M times C times delta T. What's my mass here? My mass is 100.95 grams. My steam, remember that's going to be heating the steam up 2.01 joules per gram degree Celsius. And we're going from negative 16.25 to 0. So we're going to have 100.95, 2.010 joules per gram degree Celsius, 16.25. My grams cross out, my degrees Celsius cross out and left in joules. 5 sig figs, infinite, 4 sig figs. Answer is going to be 3,297 joules. Now we're at that melting point. So Q of F is equal to M times C of F. So we take 100.95 grams, mass doesn't change. C of F is 336 joules per gram. Grams cross out, left in joules. 5 sig figs, infinite sig figs. We get 33,919 joules. Now we're going to heat the water from 0 to 100. So Q of water, M times C of times delta T. Mass doesn't change, still 100.95 grams. 4.184 joules per gram degree Celsius. Specific heat of water. And then we're going from exactly 0 to exactly 100. So that's exactly 100 degrees Celsius. Infinite sig figs, 5 sig figs, 5 sig figs, that's the number given. Infinite, that's a constant. Exact numbers. So therefore, we're going to get 42,237 joules. Now we're going to boil that water. So we're going to take Q of V. It's going to be M times C of V. So again, the mass doesn't change, 100.95 grams. C of V, 2,270 joules per gram. Multiply through 5 sig figs, infinite sig figs, grams cross out. We get 229,160. Remember, we have to go to 5 sig figs. That 0 rounds up, joules. Now we're going to heat the ice. So Q steam, M times C times delta D, 100.95. The C of ice is 2.00 joules.
I said it twice to better pause. It's Q of steam, C of steam.
Degrees Celsius, and we're going from 100 to 145.97, so that difference is 45.97. 4 sig figs get 9,281 joules. Add them all up. Last field column, answer is 317,894 joules. All right, awesome. Now, we do have one other concept we're looking at here, and that's heat capacity. This is the amount of heat that's absorbed per change in temperature. So inside the calorimeter that we do, when you run the reaction, some of the energy is going to go into the calorimeter. That's what we call heat capacity. So it's a constant we're going to find, a value going to find for the reaction. The way we find that, so the energy of the reaction is the capacity times the temperature change. Okay? So here's a problem. Determine the heat capacity of a calorimeter. If 50.0 milliliters of water in the calorimeter starts at 21.4 degrees Celsius, and after 50.0 milliliters of water is added, the final temperature. So we're doing basically the amount of energy, that temperature change, and we're seeing how much difference is lost in the calorimeter. So what we're going to do here, to find the capacity, we want to take the Q of the hot water minus the Q of the cold water. We're going to find the absolute values so that it's not a value of negative or positive. And we're going to divide that by the temperature of the cold water because the cold water is in the calorimeter to start with. So when we do that in this problem, Q of hot, remember we said it was 50.0 grams, because 50.0 milliliters, a gram is a milliliter, it's density of water. So if heat is water is 4.184, and if we take cold water from 40.7,
it's hot water,
to 21.4, the difference there is, the difference there is 15.2 degrees, is that right? That's the hot water, I'm sorry. 55.9 minus 40.7 is 15.2. Now the cold water, so we get a value, of 3,190. We only have 3 sig figs. All right, for the cold water, M times C times delta T. Again, the cold water is also 50.0 milliliters. So it's 50.0 grams because the density of water is 1 gram per milliliter. So if I have 50.0 milliliters, I have 50.0 grams. Oops, hit the button. It's 50 water, but now this is where we're going to take 55.9 minus 21.4, the difference 19.3, multiply those through, and we're going to get 4,040 joules. We subtract those, we get a negative 860 joules, absolute value, and that's going to have a bar on top because remember last field column, 0 there. So we end up with 3 sig figs, and the cold temperature, we said the difference there was cold was 19.3 degrees Celsius, divide them through. So that means for this calorimeter, every degree Celsius is going to absorb 44.6 joules, and that's the capacity of this calorimeter. Now, that's the answer there. We're going to use that value in a problem. We're going to find the amount of energy needed to release in a reaction. It takes place in the calorimeter, using the last problem. When the reaction takes place, 75.5 grams of water into the calorimeter goes from 24.9 degrees Celsius to 51.9. So what are we going to do here? We're going to take the Q of the reaction. So that's going to be the Q that goes into the water plus the Q of the calorimeter. So if we do the Q of the water first, we said 75.50 grams, M times C times delta T, 75.50. So the heat of water is still 4.184. And if we take 51.9 minus 24.9, we get a temperature change of 20.70 degrees Celsius. Multiply that all through, we get 8,533 sig figs. for my Q of water. Now, how much energy went into the calorimeter? We're going to take the Q of the calorimeter. We said that was the capacity times the temperature change. The capacity from the last problem we said was 44.6 joules per degree Celsius. Temperature change is still 27.0 degrees Celsius. Multiply those three together, we get 1,200 bar over the first number, 0. Add them up, and we get 9,730 joules or 9.73 kilojoules. Would also be correct. All right, so let's do one more problem. Pause this on your own. Calculate the energy of the calorimeter with a heat capacity, so I'm going to give it to you this time, of 32.95 joules per Kelvin, or 32.95 joules per degree Celsius. If there is 45.95 grams of water in the calorimeter, after reaction temperature, calorimeter goes from 20.50 degrees Celsius to 27.80 degrees Celsius. If you want to, pause it, try it on your own. If not, ready? Here we go. So let's do again, Q of water plus Q of the calorimeter. Q of water. We're going to take 45.95 times 4.184 times the difference between 27.80 and 20.50, and the difference there is going to be 7.30. All by together, we get 1,400 joules bar over the 0. The capacity be Cp times delta T, 7.30 times 32.95, 3 sig figs, 241. Add those up, we get 1,641 joules, and that's my answer. All right, that's it. We're going to practice these tomorrow. Any questions, remember to send me an email. That's it. Take care. God bless. Bye.